Yet another theory concerning cosmology: the universe might be a giant loop, according to a study. What shape is space? Everything we think we know about the shape of the universe could be wrong. Instead of being flat like a bedsheet, our universe may be curved like a massive inflated balloon, according to a new study. That's the upshot of a new paper published recently in the journal Nature Astronomy, which looks at data from the cosmic microwave background, CMB, the faint echo of the Big Bang. But not everyone is convinced. These new findings, based on data released 2018, contradict both years of conventional wisdom and another recent study based on that same CMB dataset. If the universe is curved, according to the new paper, it curves gently. That slow bending is not important for moving around our lives or solar system or even our galaxy, but traveling beyond all of that, outside our galactic neighborhood, far into the deep blackness, and eventually moving in a straight line, you will loop around and end up right back where you started. Cosmologists call this idea the closed universe, quote unquote. It's been around for a while, but it does not fit with existing theories of how the universe works. So it's been largely rejected in favor of a flat universe that extends without boundary in every direction and does not loop around itself. Now, an anomaly in data from the best ever measurement of the CMB offers solid but not absolute conclusive evidence that the universe is closed after all, according to the authors. University of Manchester cosmologist Eleonora Di Valentino, Sapienza University of Rome cosmologist Alessandro Melchiori, and Johns Hopkins University cosmologist Joseph Silk. The difference between a closed and open universe is a bit like the difference between a stretched flat sheet and an inflated balloon. Melchiori told Life Science, and in either case, the whole thing is expanding. When the sheet expands, every point moves away from every other point in a straight line. But when the balloon is inflated, every point on its surface gets farther away from every other point. The balloon's curvature makes the geometry of that movement more complicated. Melchiori said, this means, for example, that if you have two photons and they travel in parallel in a closed universe, they will eventually meet. In an open, flat universe, the photons, left undisturbed, would travel along their parallel course without ever interacting. The conventional model of the universe inflation, Melchiori said, suggests that the universe should be flat. Rewind the expansion of space all the way to the beginning, to the first, 1 billion, trillion, megallion second after the Big Bang, according to that model, and you'll see a model of incredible exponential expansion as space grew out of that infinitesimal point in which it began. And the physics of that superfast expansion point to a flat universe. That's the first reason most experts believe the universe is flat, he said. If the universe is not flat, you have to fine-tune the physics of that primordial mechanism to make it all fit together, and redo countless other calculations in the process, Melchiori said. But that might end up being necessary, the authors wrote in their study. That's because there's an anomaly in the CMB. The CMB is the oldest thing we see in the universe, made of ambient microwave light that suffuses all of the space when you block out the stars and galaxies and other interference. It's one of the most important sources of data on the universe's history and behavior because it's so old and so spread throughout space. And it turns out, according to the latest data, that there's significantly more gravitational lensing of the CMB than expected, meaning that gravity seems to be bending the microwaves of the CMB more than existing physics can explain. The data the team is drawing upon comes from a 2018 release from the Planck experiment, a European Space Agency ESA experiment to map the CMB in more detail than ever before. The new data, to be published in forthcoming issue journal Astronomy and Astrophysics, it's available on the ESA website, Both Di Valentino and Melchiori were part of that effort as well. And to explain that extra lensing, the Planck collaboration tacked on an extra variable, which the scientists are calling A lens, to the group's model of the universe foundation. This is something that you put there by hand, trying to explain what you see. There's no connection with physics, Melchiori said, meaning there's no A lens parameter in Einstein's theory of relativity. She said, what we found is that you can explain A lens with a positively curved universe, which is a much more physical interpretation than you can explain with general relativity. Melchiori pointed out that his team interpretation is not conclusive. According to the group's calculations, the Planck data pointed to a closed universe with a standard deviation of 3.5 sigma, a statistical measurement that measures about 99.8% confidence that the result is not due to random chance. What's well short of the 5 sigma standard physicists usually look for before calling an idea confirmed. But some cosmologists said there were even more reasons to be skeptical. Andre Linde, a cosmologist at Stanford University, told Life Science that the Nature Astronomy paper failed to take into account another important paper published on the ARXIV database. In that paper, University of Cambridge cosmologists George Efstathiou and Stephen Grattan, who both also worked on the Planck collaboration, looked at a narrower subset of data than the Nature Astronomy paper. Their analysis also supported a curved universe, but with much less statistical confidence than Di Valentino, Melchiori, and Silk found, looking at a larger segment of the Planck data. However, when Efstathiou and Grattan looked at the data together with 2 other existing datasets from the early universe, they found that overall the evidence pointed towards a flat universe. Asked about the Efstathiou and Grattan paper, Melchiori praised the careful treatment of the work, but he said the duo's analysis relies on too small a segment of the Planck data, and he pointed out that their research is based on a modified and in theory improved version, the Planck data, not the public data set that more than 600 physicists had vetted. Linde pointed to that reanalysis as a sign that Efstathiou and Grattan's paper was based on better methods. Efstathiou asked not to be directly quoted, but pointed out in an email to Life Science that if the universe were curved, it would raise a number of problems, contradicting those other datasets from the early universe and making discrepancies in the universe's observed rate of expansion much worse. Grattan said he agreed. Melchiori also agreed that the closed universe model would raise a number of problems for physics. He said, I don't want to say that I believe in a closed universe. I'm a little bit more neutral. I'd say let's wait on the data and what the new data will say. What I believe is that there is a discrepancy now, that we have to be careful and try to find what is produced in this discrepancy. This is by Rafti Letzer on Life Science. It's Embedded Reality. Please leave your comments. Thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.